Our next speaker is Professor Junwu Tu from Shanghai University of Science and Technology. His topic is from geometry to categories and back. Let's welcome.
Okay, thank you for the introduction. Thank you. I should thank you for the organizer to having me here, so that I have this opportunity to present some of our latest works. I'll talk about essentially category theory. I'm an algebraist person by heart, and but it's I think the interesting thing also from the previous talk is to see that all these abstract concepts has applications in physics as well. Okay, so right, let's start. Okay, so I'll begin with my motivation for doing this categorical theory, and the story is begins with mirror symmetry. So I think maybe a lot of you know better than me. So the physicists, there were four physicists computed Gromov-Witten invariants, which count rational curves in a quintic hypersurface. And the way they calculate this invariant is by using a completely different space, a so-called mirror dual family of Calabi-Yau, but also study something not related at all to Gromov-Witten invariants, so-called variation Hodge structure. It's a classical topic in complex algebraic geometry. So that was a very surprising calculation for mathematicians. And so I call this version of mirror symmetry enumerative mirror symmetry. So it basically conjectures equality in a very precise way that Gromov-Witten invariance of some space X is equivalent to variation Hodge structure on a dual Calabi-Yau space. Okay, so this is the mysterious calculation. I call the left-hand side A model and the right-hand side B model. So A model is for symplectic geometry, B model is for algebraic geometry or complex geometry. And later in 1998, Kontsevich in his famous ICM talk proposed this homological mirror symmetry conjecture, which is supposed to explain the enumerative mirror symmetry from physics. The conjecture is about equivalence of two categories. On the A side, so it would be Fukaya category of Lagrangian submanifold. And on the B side would be the derived category of coherent sheaves, or the category of holomorphic vector bundles. And these are the examples of Calabi-Yau categories that I'm mainly interested about. So Yau was here, but he's not here now. So he's differential geometry, geometer, but now we also name categories after him. I think both Calabi and Yau probably don't care so much about categories. But anyway, so I think it's yeah. So this is a natural way to see. I'll talk about this more later. Okay, so so Kontsevich suggests that this categorical equivalence will imply the enumerative mirror symmetry conjecture by the physicists, and the construction from a category. How do you get some invariance? When you apply it to Fukaya category, you're supposed to get Gromov-Witten invariance, and that's the main focus of today's talk. So there are also other motivations to. So I call this categorical enumerative invariance, and I mentioned one motivation for doing this. Then there are also other motivations. For example, construction of higher genus B model invariants for Calabi-Yau spaces. So in the classical enumerative mirror symmetry, the equivalence is for Gromov-Witten invariance in genus 0. And the right-hand side is variation Hodge structure. But Gromov-Witten invariants are also defined for higher genus. And so you could ask why, what's the mirror invariant in the B model? And that's not clear so far. And so that's using categories is one way to do it. And the other way is, the other motivation could be, so there are a lot of Calabi-Yau categories that are not from Calabi-Yau's categories. For example, I'll mention this more later. So you could have like a non-commutative K3, which is category, Calabi-Yau category, but not from Calabi-Yau's K3 surface. Okay, so the construction of this categorical invariance has some literature. So from 2001 to 2010, roughly, Kontsevich group of people works on the foundations of this, what they call non-commutative geometry of Calabi-Yau categories. And so they laid a lot of foundational work that we will be using. And around 2004 and 2005, Costello wrote 2 papers, basically define this invariance for Calabi-Yau categories. His definition is a bit of abstract, and so not very explicit. So what we did recently, more recently, not so recent now, but what we did was to give an explicit combinatorial formula for Costello's invariant. So also kind of explain his paper in a more transparent way. Okay, so how does it look like? So we'll start with a category A, which we assume it's smooth and proper. All this language is from Kontsevich, this foundational work. They define what smoothness means for a category and what properness means for a category. And we always work over a field of characteristic 0. And you could also talk about volume form, holomorphic volume form for categories. And so that's also part of their work. And another input data, which is not so, so this is the splitting, a choice of splitting of the Hodge filtration. Okay, so I'll say more about this later. So after we are given these 3 pieces of data, we get numbers. And these numbers look like Gromov-Witten invariants. So it will depend on the 3 pieces of data, depend also on genus and an integer n, which is the number of marked points. And these insertion classes, alpha 1, alpha n, are in the so-called Hochschild homology of A. And these U, K1, Kn, they are analog of psi class insertions in Gromov-Witten theory. Okay. So they look exactly like Gromov-Witten invariants, but constructed from categories. And so I'll briefly sketch the construction of these invariants, just to get a feeling of what it looks like, what are we really working with. So conceptually, so I'll talk about the main idea behind the construction is by Kontsevich and Soberman and Costello and Lurie. So you see also this name from previous talk, that conformal field theory. We added a topological to mean that we take chain complex. So this C lowest bullet means chain complexes on moduli space of curves in genus G with K incoming marked point and L outgoing marked point. So you have home. So K's are inputs, L's are outputs. And this framing means in conformal field theory, you could have boundary marked point. And that rotation by S1 is a framing, so-called framing. Okay. So basically, this framing means more rigorously, it's a coordinate system, a choice of coordinate system around each marked point. And this coordinate system is almost contractible, except the leading coefficient can be rotating by an angle, EI theta. So if you are given a category A and a volume form on A, they construct you a representation, an action of chains on moduli spaces of curves to the Hochschild chain complex. Okay. So it's an action. So this is like more like Atiyah's definition of topological field theory, but we have conformals. So we have moduli spaces. The families of surfaces act on this chain complex. So this is the first main ingredient. Now to get invariance, we want to have fundamental class. But this M frame GKL, they are smooth surfaces. So there's no fundamental class. So that's the next thing. So it turns out that the main idea, actually, this is the second part, is a splitting data S fixes for you an extension of this action to the Deligne-Mumford compactification. And once you are compactified, you can take its fundamental class and get invariance. And that's more or less indeed what happens. And so what we get is an explicit formula describing this fundamental class in terms of so-called Zenz-Weibach string vertices. So you see the point is here is the construction of fundamental class in this process appears first we already have the open part of this moduli space. And using S, we extend this to the compactified moduli space. And so when we describe this fundamental class of this Deligne-Mumford compactification, we will be using some chains in the uncompactified, the smooth part, together with some data depending on the splitting on the boundary, on the compactification part. And this process actually works for any topological conformal field theory with a homotopy trivial circle. Any topological conformal field theory comes from with a circle action because this reparametrization of these marked points, this homotopy circle. So if that circle action is homotopy trivial, so namely in homology is 0, then we get this construction works. And so in real life, it's more complicated than what, this is a rough idea and it's very helpful, but what we really work with is a combinatorial model for this Zenz-Weibach DGLA. I denote by, this comb is for combinatorial. And so we get these combinatorial string vertices. These are the chains in the smooth part. And so we use the language differential graded Lie algebras. So Kontsevich, Soberman, and Costello and Lurie's construction gives you a map of DGLAs from this Zenz-Weibach DGLA Lie algebra to some analog of the differential graded Lie algebra constructed algebraically from the category. And the last part is using the splitting data, we can trivialize this Lie bracket. So the Lie bracket is defined using the previous circle action. So if the circle action is homologically trivial, then we can trivialize it. This is a lot like in Tian-Todorov theorem. You have a de Rham operator, which in homology is 0. And the Lie bracket governs this deformation theory of Calabi-Yau varieties. But then if it's 0 in homology, so you can trivialize it. And that's why obstruction is, Calabi-Yau deformation is unobstructed. And you can make, actually this is very related to this Calabi-Yau Tian-Todorov theorem. Okay, so we construct similar to Kontsevich formality, we construct this formality given a splitting data. So this helps you to give a specific splitting data. We can give a particular trivialization of this Lie bracket. This is circle action. And then this invariants, categorical enumerative invariants, CEI, are given by the push forward of this Morand-Cartan. So we have a Morand-Cartan in this moduli space of curves that we can prove it's unique up to gauge equivalence. And then we push forward to the algebraic thing, and then we trivialize the circle action. Okay, so this gives you the invariance. So note that this on the geometric side, you can't really trivialize in the moduli space of curves because these are actually coordinate systems. The circle action is not trivial at all. They are coordinates on the Deligne-Mumford space, angle coordinates. So in the end, we get combinatorial formula for this invariance. So I give you some I know this is a bit of jumping in logic, but I'll just give you an idea of what we really get in the end. So the genus 1 invariant for a category, depending on the 3 pieces of data, this one means genus 1, this next one means 1 marked point. So it will be consists of 2 parts. The first part coming from a chain in the smooth moduli space. The second part comes from some contribution from the degenerate nodal elliptic curve. And the first string vertex is given explicitly by, so this vertex here is what is a string vertex and given by some so-called ribbon graph, linear combination of ribbon graphs. These things that you can really evaluate on Hochschild chains to get a number. And this vertex is 1 input, 2 output, and we have explicit combinatorial form for that. So you can, the point of the writing down this is that you can really implement it in a computer and compute these invariants. Okay, so I mentioned a little bit some immediate consequences of constructing these invariants. So you could hope that this gives a new B-model invariants when we apply the construction to the category of G-equivariant matrix factorizations of a potential function W, then these invariants are conjecturally mirror symmetric to FJRW, Fan-Jarvis-Ruan-Witten invariants in all genus. And this construction was not known in literature before. So what's the B model and mirror to the FJRW was not known in the literature. Well, I should mention this. We defined it, but it's not so satisfactory because it's not very computable. The computation is pretty hard. Okay, that's why maybe people have not really go into computing these invariants for these categories. And the second thing, so is we can apply the construction to the derived category of coherent sheaves on a smooth proper Calabi-Yau space. And that's a Calabi-Yau category. And these invariants are conjecturally mirrored to higher genus Gromov-Witten invariants, like from the beginning of this motivational part of mirror symmetry. And these are new also. It was not, so in physics, there are literatures BCOV construction, known as BCOV construction. And there are much more categories that you can come up, Calabi-Yau categories. I mentioned one example. You can take X a cubic fourfold, for example. And then it has a canonical component called Kuznetsov component. And that's a Calabi-Yau, 2-dimensional Calabi-Yau category. Sometimes it's not geometric. And its being geometric is conjecturally equivalent to X being rational. And so it's an interesting thing to calculate these invariants for this Kuznetsov component. Okay, so I mentioned I mentioned already these invariants are difficult to compute, but there are some computations. In the case when genus 0 and n equals 3, so this is a 3-point function, and you see from the previous talk this Frobenius algebra. Okay. So any Calabi-Yau category A, its Hochschild cohomology is a Frobenius algebra. And you can compute it. And that's this genus 0, 3 categorical invariants are exactly structure constants of this Frobenius algebra. Right, so 3 point. In genus 1, when the A is the ground field, Costello computed it, and Caldararu and me. Caldararu is my collaborator and also my former PhD advisor, so we computed it. In the case of elliptic curve, so we take a derived category of coherent sheaves on a smooth elliptic curve, we can compute it in genus 1, and that indeed matches with mirror symmetry. And in the case of, we can also compute this for matrix factorizations, and that's in genus 1, that's done. Okay, so in genus 2, there's essentially this for non-trivial target, so polystruct A infinity algebra on elliptic curve. This is Chen's thesis work to appear. And for any Gn stable, I show that the Ci of the ground field matches with Gromov-Witten invariance of a point. Okay, so that shows some evidence of this relation with Gromov-Witten theory. And for any Gn stable, and if you take an associative algebra, so no, we talk about A infinity category, but if you can just take one associative algebra, we still assume it's smooth and proper. And in this case, it's so-called topological theory. So you can reconstruct it from, essentially it's a combination of this ground field case with the Frobenius structure of A. Okay, so this is some computations. And in the next part, I'll mention something that I've been working on lately. So we mentioned the B-model invariants. So the setup is we take X to be a smooth projective Calabi-Yau threefold over complex numbers. And then we take our category AX to be a DG enhancement of the category of coherent sheaves. Okay. So it looks like we have a choice here, the DG enhancement. But actually, there's a theorem by Luntz and Orlov says this enhancement is unique. So there's no choice. It's there's a unique differential graded enhancement. And we take a holomorphic volume form on X. And so we know comparison theorem. So comparison means geometric theory and non-commutative theory. If you take a holomorphic volume form in the sense of Calabi and Yau, right, geometric volume form, holomorphic volume form, we do get a non-commutative volume form on the Calabi-Yau, on the category AX. And for the splitting data, we can take the complex conjugate splitting of the Hodge filtration. Okay. So this is also a classical, so this is just a PQ decomposition, right? So you have HPQ of X, right? So its conjugate is HQP. Yeah. So if we take this complex conjugate splitting geometrically, and it's another comparison theorem proved by Blanc that you can, this complex conjugating geometrically defined is actually categorical. So given this category AX, it has a canonical splitting of its Hodge filtration, non-commutative Hodge filtration. Under this comparison, it compares with the geometric complex conjugate splitting. Okay. So there's a canonical one. So we'll take this one. If we take this one, I'll call this invariance B-model categorical enumerative invariant. And because S is canonical to the category AX, you see here, I deleted S from the notation. So it's independent of S. It's canonical to the category AX. So in particular, as part of these numbers, this uses dimensions 3. So because if it's not dimensions 3, this number is 0. It just by degree reason. And so we get a number for each genus, a complex number for each genus. This categorical invariance provides us. And we want to also get rid of the volume dependence. So we can show that if you scale, so because the volume, holomorphic volume structure on X is only one dimensional. So different choices of volume is up to a scalar. So if we scale this lambda, we know the invariant scale by lambda to the power 2 minus 2g. And so we can motivated from this, we can take fractions of these invariants. So I skipped the labeling, the indices AX and omega in these fractions. If we can take F2 square over F3, for example. If we scale lambda, this F2 square scales by, I think, lambda to the -4. And F3 scales also by lambda -4. And so these are independent of omega. And similarly, you can take other fractions like this. It will be also independent of lambda. So it only depends on AX. Okay? So if you make this more rigorous, well, what you could do is you can take this graded ring freely generated by these variables Ti in even degrees. So the weight of Ti will be I. And you take rational functions in this ring of weight 0. Okay, so just like in the previous examples. Then we evaluate this Ti by appropriate genus. Okay, or this categorical invariance. And then this invariant gives you a derived invariant of X. Okay. And so the content of this theorem is that it's only depend on the derived category of X. It's a derived invariant of X. So as I said, this uses the Luntz-Orloff theorem. Says DG enhancement is unique. And what we prove is this Morita invariance. Okay, so this also a new birational invariant of X. So this is a theorem due to Bridgeland. Bridgeland proved that in dimension 3, derived invariant, birational equivalent X Calabi-Yau threefold implies derived invariant equivalent. So if you are derived invariant, it's automatically birational invariant. So in the physics literature, actually it goes, so there was a proposal to prove give counterexample of Torelli theorem for birational Torelli theorem, which uses genus 1 invariant. Okay, so this so if we vary X, so for each X we get a birational invariant or derived invariant of X. If we change X, these FTs are functions. They are rational functions. They might be 0, so you can, because there's a denominator. So they are rational functions on the moduli space of Calabi-Yau threefold. And this should remind, so this is, I will consider this as a kind of analog of this for dimension 1. You have the analog of elliptic curves. You have modular forms. And modular forms, they scale in a appropriate way when you, so this should be the analog of this in 3-dimension Calabi-Yau threefold case, the analog of modular forms. And it's related to this finite generation property. Right, so in the Yamaguchi-Yau's work, they take this Fg divided by appropriate powers of, in the paper it's called C to the 2g minus 2. C is like genus 1 invariant, genus 0 invariant. And that is an element in this, this kind of ring. And so, yeah, so there's finite generation related to finite generation in Yamaguchi-Yau. Okay, so I mentioned work in preparation with a joint work with Shen Yefeng. So what we prove is if we consider this B model categorical in CEI, like I just defined using the complex conjugate splitting, if we consider it in a family, so we are given a miniversal family, means the Caldararu-Spencer map is an isomorphism. And we still assume it's smooth and projective. Then we can have a family of invariants. So it will depend on the base M. And this relative B model categorical enumerative invariants satisfy BCOV's holomorphic anomaly equation. Yeah. So we are working on this, should appear this year. This gives some evidence of the a proposal of Costello, which he proposes to define bimodal topological string partition function using categorical invariants he defined. Right. So this is quite a, I think this is a quite a, like from my title, this is quite an interesting thing, because on the one hand we are doing very algebraic things and category theory. On the other hand, they're actually useful, not useful, but at least appears in string theory, right? Yeah. So another evidence for supporting the definition to define the bimodal topological bimodal using categorical invariant is we can also prove this Witten's quantum background independence. So Witten wrote a paper, quite a beautiful paper, on his interpretation of BCOV's holomorphic anomaly equation as quantum background independence of string theory. What does it mean? So you see, string theory depends on the Calabi-Yau background. And what Witten proves is the invariance, topological string partition function, is independent of the background up to continuous deformation of complex structure. Okay. So on a connected component of complex structure, it's independent. And this independence is equivalent to holomorphic anomaly equation with insertions. So previously I was mentioning this work, it's about Fg itself. So it's about this this Fg with no marked point. But in BCOV, there's a more general version of holomorphic anomaly equation which depend on marked point. So this is a holomorphic anomaly equation with insertions. And this version of this holomorphic anomaly equation, Witten interpreted as this independence of background Calabi-Yau deformation. Okay, so more precisely, in the process of writing up this work, is given again a miniversal family of Calabi-Yau threefold, and let's consider this M tilde, the total space of the C-star bundle associated to the relative line bundle, canonical line bundle. So it's a long to write it, but this M tilde is just the moduli space of a Calabi-Yau together with a volume form, okay, on it. Yeah, so this is what M tilde is. Then we can construct a Fock bundle over M tilde. So this Fock bundle seems, so I didn't write more details of this, but it's just symmetric powers. So it's a C infinity vector bundle, and it's completed symmetric powers in 1-0 type forms on M tilde. Okay, so this is what the Fock bundle is. And this Fock bundle, if so this second part is basically, so in physics or in math it's called special geometry. In physics it's called TT star geometry. Okay, if you use that, so there's a being Calabi-Yau, this moduli space has a particular geometry associated to it called TT star geometry, and from there you can construct a projectively flat connection on this Fock bundle. This is this part is very canonical, very differential geometric, a classical differential geometric. Now the main point of this theorem is we can use the B-model CEI to cook up a canonical section of the Fock bundle. Okay, this is what in physics called this B-model topological string partition function. So this is generating function for the CEI. And the quantum background independence, according to Witten, is when you move this. So you can define this pointwise on the moduli space M tilde. But when you move it along the moduli space using the projectively flat connection, it's almost flat. It can't be flat because the connection itself is projectively flat. So it's as best flat as possible. So when you move back, so if you do parallel transport, when you move back, it's up to a constant. Okay, so this is the so that's why that's how Witten formulate quantum background independence. It's a constant section, and it's a very interesting observation. I think there's something to explore because Witten were motivated from his motivation was this analogy between so-called three-dimensional Chern-Simons theory with the structure appeared there and the structure appeared here. So in the mathematically, there's works of this 3D mirror symmetry. I think it's related to, so these people work on representation theory. They're related to this kind of, you also see these kind of structures. Okay, so in the end, I mentioned work in progress with Lino Amorin. So we want to we want to obtain so-called open-closed categorical enumerative invariants. So previously, the CI, they are closed invariant. They are Gromov-Witten invariant. They can't close Riemann surfaces. There also some interest in computing open Gromov-Witten invariants. So this is even in the literature of symplectic geometry, computing or defining open invariants is a pretty hard problem. There's only very limited cases that you can show that it's defined. So, and there's also another name called the real Gromov-Witten invariants. They are essentially equivalent. When they are both defined, they are equivalent. But they are both limited. For example, I think the people compute like CPN and RPN, and essentially all this sort of stuff. Okay, so in the FGRW story, open FGRW invariant, there was some very limited work where you take the potential to be AN singularity, so XN potential like XN, and then they recently claimed some work of XA plus Y to the power B. So this is where we are in A side. So we are not really into a comparison of open invariants in the A side, but really just try to see in the categorical framework what we could do. Okay. So you see that it's also very constrained. But I think the main advantage for us is we have a more systematic way of understanding or defining these invariants. We see the abstractions, and once we assuming the abstractions are 0, then we can define it. And that's the status. Okay, so the first work is to generalize the previous this Zenz-Weibach. So in the construction of CI, the most important ingredient are these Zenz-Weibach. Also, two physicists work in stream field theory. They also talk about open-closed stream field theory. So we do it combinatorially. So everything is explicit in terms of these ribbon graphs that I drew. So what we did in the first, well, this is also work in preparation. So what we did is we defined a open-closed L-infinity algebra. So I denoted this comp open-closed. This contains the previous combinatorial Zenz-Weibach DGLA as a subalgebra. And we show that this one, after fixing the two initial conditions. So this one was from the closed part. This one, the only new one is from the open part. This 0 means genus 0, one boundary component. B means boundary component. M means interior marked point, and M is the boundary marked points. It's a vector depending on the boundary component. So in this this M should be 1. So yeah, so we have one open boundary. So if we fix the 2 initial data, it determines uniquely open-closed string vertices. Okay. So yeah, so there's up to gauge equivalence. There's a unique Monod-Cartan element in the open-closed L-infinity algebra. Okay, so that's the first step. The second step is like just like in the previous construction. So we need to trivialize the circle action. But in the open case, we not only need to trivialize the circle action, because there's an open boundary. The boundary condition is given by a prescribed object in your category. Let's call it E. And in the symplectic work by Solomon's group and Zinger's group, they need to assume some condition on the Lagrangian. In Jake Solomon's group, they need to assume this E is homologously trivial. So you can find it's a boundary of something in high dimension. So in our framework, this means it's Chen character, which is a non-commutative geometry, means identity element in the negative cyclic homology is trivial. Okay? And so we make this assumption, and so then if it's trivial, we can find an element H so that to trivialize this identity element. And that's what we use to trivialize boundary insertions. So our open-closed invariant will depend on 2 pieces of choice: the splitting, as in the closed case, and the open part, which is the trivialization of the object, the Chen class of the object. And so what we get is a systematic way to define invariants with this tuple of A, E, omega. Omega is a volume form, E is object, S is splitting, H is a trivialization of the Chen character of E. Here, systematic way means for each, if you tell me the combinatorial number that you want to get, G, N, N, and this M vector, then I tell you where are the obstructions. What you need to assume is 0, and then if it's 0, you can assume, you can define this invariant. The resulting invariant will depend on the splitting and the choice of H. And so you can, so in the second part, so if your Lagrangian or your object is a homology sphere in odd dimension, so it means the self-X is in the category is only 2-dimensional in homology. There's identity, there's just one odd guy in some other dimension. Then it's defined in all genus. Okay. So this basically is a simple situation where you can verify all the obstructions to define these invariants are 0. Okay. We can do a bit more examples, like in the open-closed FGRW story. Even though you are not homology sphere, then there are situations where you can still make this well defined. Okay, so I think it seems like we are a bit ahead a little bit ahead, not too much, to define open invariants comparing to the geometry groups. Yeah, so that's I think that's the end. I'll stop here. Thank you.